Hi, my name is Jaspal. I'm an engineering technologist here at EECS. That's my email there. So we are just going to go over a quick, short Verilog introduction, basically how to design a simple CPU in your labs. So that's the idea of this presentation and recording. So you guys can, hopefully understand and do your labs in a better manner. So the agenda for this presentation is, top level review of the CPU. We're going to do this presentation in two parts. The first part is this one. So I'll be covering the top level review of the CPU, and then in this part I will go over the individual building blocks, how the CPU is going to be built. So the two type of blocks we'll be using are combinational blocks and sequential blocks. So I'll be going over those blocks later on. And in the next part of the video, I'll go over how to do the interconnection of all these different blocks and how to do a simulation of the full CPU at the top level. So let's get started. So first of all, acknowledgements. To prepare this presentation, I've collected information from various resources, including from our past labs and from the internet. So I'm acknowledging that, and everywhere possible, I've given due credit in the slides. You will see that. Also note that I'm using in this presentation and this recording, I'm using a Verilog compiler called Icarus Verilog, which is long for iVerilog, version 9.7, available on online free simulator called EDA Playground. So you guys can also use this. It's a free simulator, but it does require a registration for you, I think, particularly if you want to save your files there for later reference. So you may want to do that. Otherwise, I think you can just go there, run your code, and see the results. But I would definitely recommend registering. And like I said, you can save your files and you can come back a few days later and whatever, and play with the code again. So this same code is expected to run fine on the iVerilog tool, which we are using on ECS computers. I've tried a couple of snippets of code, couple of files, few files, and they all run fine. So I think all the code that I'm going to be referring in this presentation and this recording, you should be able to run there. So let's get started. So the CPU at the top level, at the end of this, by the end of the labs, by the end of the course, the CPU that you will be basically designing will be looking something like this. It can be intimidating a bit, particularly if you are new to this kind of a hardware. But what we can do is, what we will, I recommend, and usually the proper way to do is to divide the, module or big design into smaller blocks. So let's see how we can do that. So as we can now, a couple of things before I get into that to keep in mind. Instructions in this architecture, which is basically based on the RISC-V architecture, which you guys have used in the first term of the course. The instructions are 32 bits wide, and the data and the data registers, they're both 64-bit wide. So keep that difference in mind, and these two instructions here. So that's why when we are updating a PC, which is pointing to the next instruction, we always increment it by 4, as you can see it here. But when we are actually in the data side of the memory, when we want to read data from the memory or write data to the memory, then the address, which is here, is 64 bits wide. And here, and the address is incremented by 8. So just like in the PC, we keep the last 2 bits 0 because it is incremented by 4. Here, because we increment by 8, so the last 3 bits are kept 0. as you learn binary numbers more, you will better understand the concept, why these two zeros imply that we are incrementing by 4 and these 3, because 2 raised to the power 2 is 4 and 2 raised to the power 3 is 8. That's basically the reason for this. All right, so let's start looking at this big design at like a smaller level, at smaller blocks, which will help do the lab. So you guys will be doing your labs where you start with some adders, some multiplexers, then you build some registers and then memory blocks. So that's and then at the end of the lab, at the end of the term, you'll be putting all those things together, interconnecting them and making a CPU like this. So one of the first block we can narrow down is the PC section. And like I said, PC is used to point to the next instructions. This would typically be a read-only memory where the instructions are stored, and you always have to, the PC will point to the next instructions to be read from this memory. So the hardware, how to increment PC, and the PC, like you may remember, it could be the next instruction, or it could be the instruction many instructions later, like if in case of a branch or in case of a jump. So so you can see, so current PC is this, which is coming from this register, which is I'll talk more about registers in a while. So so current PC value is coming from there, and the next PC is coming, current PC added with 4. So this is an adder in terms of this is all hardware we are talking about now. So this is a adder which adds 4 into the current PC and gives you the next PC. So typically you would be, typically you'll be getting next PC here. But in case of branches or in case of jump instructions, you would be getting an immediate value, which you'll be adding to the current PC. So in that case, and this would be the control to select that value. So PC could be either next PC, or PC could be the current PC plus the branch offset, which would be coming from this section. You see this black line coming here and shifted by 2. I think this should be shifted by 2 actually. I think there's a typo there because of this reason I mentioned. All right, so let's see. So this is one block, how to make a hardware block, which basically relates to the PC and the next PC task. So from the instructions which we are reading from this memory, which is basically a read-only memory. The instructions would be, if you remember using your green sheet, RISC-V green slide, which has been provided to you guys. The instructions is made up of, different sections. Some of them like point to source register 1, source register 2, the destination register. So that depending upon the type of instruction, like I mentioned in that green card, which you should be having as a good reference with you. And of course, opcode is also part of the instructions. So these instructions, as we read them, depending upon the instruction, an immediate value might be generated as per the different instructions, which should be a 64-bit value. And the opcode, which will be decoded to decide whether it's a branch operation, it is what kind of an ALU operation it is going to be. So that part is basically done here. So we have some decoders here. This would be a decoder here with the read instruction. This whole part here would also be a decoder, which reads the 32 bits instruction and then split it out into like subsections, like the address for the source register 2, address for source register 1, and like you can see, they then go to this array of registers, 32 registers, like this, RISC-V have 32 regular registers. So these are those registers here. So those addresses would be then taken from the instruction, 32-bit instruction. So this could also be a type of a decoder, along with this decoder here and this decoder here. I'll talk about the decoder in a while. So this is another section of the CPU. So let's go to another one. So here you can see we are referring to the ALU, which is the arithmetic and logic unit, which will do operations like addition, subtraction, shifting, etc. And depending upon the instruction, we may have an address here, a 64-bit address, if we are going to read or write to the memory, or that it might be a result, 64-bit result of the ALU operation. And depending upon this control bit, whether we are doing whether we are going from memory to register, or we are going from the ALU to register. So write data to the destination register is coming out from here, and it is decided whether by this bit whether we are getting that write data from the memory or we are getting the write data directly from the ALU. So that's another section of this processor from the top level. Also, we have this read and RAM memory here, read and write memory. Read and write memory. So this memory here is read only. This one we can read from and also write also to it, and that will again decided by this bit memory write. If it is high, then we do a write operation. If this is high, then we would do a read operation. So again, like I was saying, the opcoders, these will be the decoders, which this one will be decoding the instruction bit 6 down to 0, which contains the opcode, and will be deciding which bits are going to be asserted as per the instruction. Here we have a branch control, which will decide what the current PC plus branch offset is going to be, which is coming from here. And the third decoder will be for the ALU operation. So as you can see, we have some multiplexers here. We have some adders, right? In the adders in the ALU, we have registers, 32 of them. We have a memory, and we have decoders. So I'm going to now talk about these things going forward, and show you how they look like. There are truth tables, and show you the code on EDA playground, and what kind of results we get. And a good advantage of EDA playground is it also has a waveform output, so which makes it easier to see results also. All right, so let's go now to the, so now, I was talking about the opcode decoder. So it decides things like the second input to the ALU. The second input is coming from the source register 2, or is it going to be the immediate value? So if we are using, if there is an immediate instruction, so might be using immediate data, which would be coming from here. Otherwise, we might be using, as per the instruction source, the results from source register 2, SRC2. What's going to be the PC, which I already talked about a few times. It also decides what is going to be written to the destination register here through the through this bit. So result of the ALU or result or read data from the memory block. And some other controls like memory read and write control, the write control for the destination register, which is coming here, reg write, etc. So these are the other things which the opcode decoder does. All right. So now we're going to talk about these building blocks. So initially we'll be talking about the combinational blocks. Multiplexer is a combinational block. The other type of blocks are sequential. We will talk about them later. So multiplexer, a simple multiplexer is can be considered like a switch. You press the switch. If it is pressed, you have one output going, one input goes to the output. If it is not pressed, the other input goes to the output. So in terms of hardware, if you have these gates, AND gates, OR gate, NOT gate, so this is how it can be implemented structurally. So this is like a structural implementation of 2-to-1 multiplexer. So I'll show you the code and briefly behavioral code I will show you. So this is showing a 4-to-1 multiplexer. So here we had only one select input, but here we have two select inputs. So two select inputs obviously will give you 4 different values, 0, 0, 0, 1, 1, 0, 1, 1. So depending upon those, again just like a switch, either D0 would be going to out, D1, D2, or D3 as the case might be. So this is again structurally how 4-to-1 multiplexer would be in terms of hardware gates. So you can see there again there are 2 inverters, 4 AND gates, and 1 big OR gate. These are the references from where I've taken some of these images. So let me now show you the code for multiplexer. So this is, as you can see, it's a very simple code, and like I said, it's a behavioral code, and I hope you can see it. I can try to make it bigger, and but hopefully you will get the slides also, the code also. I am hoping the professor would be giving you for reference. So you can see, if select is high, the output is in A input. When select is low, the output is B input. And this would implement that OR gate. So these would be the 2 AND gates which I was showing in that slide there. And this part of the code is just the test bench here. So let me actually run this code on EDA Playground and see what do we get. So let me go to EDA Playground, which is open somewhere. There it is. And so I'm logged in. My playgrounds are saved. And I'm going to open the SMUX. So this is the same code I was showing you. So it is, and this is a test bench which is basically simulating it and trying some combinations. So let's see the results. What do we get? And this is that Verilog simulator I was telling you, and EDA Playground. You can just go to this website, register. So now let's look at the results of the multiplexer. You can see when, like I said, when select is true, which is here, so you can see the third column is select, which is this one. So when select is true, the output is same as A. So that is the case. We can see that whenever select is 1, the output is A. Whenever select is 0, the output is B. Another, good thing in Verilog, which you have to be, it's a good thing and also not a good thing. A good thing in a sense, you can see my code here is basically single bit multiplexer 2-to-1. But in the test bench, before when I instantiate the multiplexer, mux2, let me go into the other code, you will see it better. So this is the multiplexer which I instantiated, but see, I changed the size to 8. So suddenly, so this instance is now 8 bits, and Verilog allows that. So it's a good thing and a bad thing because Verilog, if you know what you're doing, it can make you more productive, help you do things quickly rather than writing a multiplexer here again with for size 8 or whatever different sizes. But it can also be a bad thing because compiler can do things which you may not understand, particularly if your design is pretty big. But anyway, so this is one way you can change the size on the go when you make a copy of the instance when you make a copy of this instance, which is through this line. So if you go back to the EDA, like we say, so the behavior is correct as we expect. So I just changed it from single bit to an 8-bit, but it's still a 2-to-1 multiplexer. Both my inputs A in and B in, they have been changed to 8 bits. All right, let's go back to our slides. So that's how you would be making multiplexers in your in the RISC CPU. So the other component we discussed there, which we saw, we had a few types, few different versions of, was the decoder. So in digital electronics, what's a decoder? Digital electronics, a decoder is a combinational logic that converts binary information from n inputs to a maximum of 2 raised to the power n unique outputs. So this is showing, this definition has been taken from Wikipedia, the reference is there, the diagram has also been taken from there, and you can see a diagram of a 2 to 4 decoder. So you have 2 input bits, and so 2 to the power 2 is 4, so you have 4 different unique cases output. So when it is both bits are 0, this bit is high, and when this one of the bit is 1, you see this bit is high, when the other one is 1, and so on. So this is how it is implemented in terms of hardware. When you compile the code and program an FPGA or make an ASIC device, application specific IC. So that's how your code would be implemented, get translated into hardware, like it's shown here. You would have, in this particular case, you would have 4 gates, 4 NAND gates, 4 AND gates, and 2 inverters. So this is like a block diagram of a 3 to 8 decoder. Same principle. You have 3 inputs, so 2 raised to the power 3 is 8. So you have 8 different unique cases. So how would you implement a decoder in a code? Let's now look at the code of a decoder. So this is the code for a decoder, and we are basically just using a case statement similar to like you guys might have used in C language. So we check the case of this variable called n, which is also an input port. So if it is 1, now you can see input is 3 bits wide, 2 down to 0, so 3 bits. So 2 to the power 3 gives 8 different combination, and you see we are not evaluating all 8. So that's why we have to use this statement called default. So default is for all those other cases which we are not evaluating. So for all those cases which are not mentioned, covered here, the output would be this value, all zeros. But for these ones which are covered here, when n is 1 or n is 2 or 3, 4, and 5, the outputs would be defined like this. So let's run this code again on the EDA playground and see what does it do, and does it behave as we expect. So we were looking at the decoder. So there's a decoder. So this is one advantage of registering on EDA playground. You can refer to your code which you have saved. Some of my code has been saved. You can see from last year it is still available. So we were looking at the 3 to 8 decoder. All right. So this is the same code like I was showing you. It has been cut and pasted from the other side. I find it easier to work in a text editor compares, and I just do my code on a text editor and then cut and paste here. Try to stick with the indenting your code. It makes it easier to read and easier to debug. So anyway, so the decoder is here. It's 3 input bits, so we could have 8 possible outputs, but we are covering only 6 of them. and this is a test bench and how to monitor those values. So let's run this code and see what do we expect. What do we see and if the results match. So let's see. So in the first case, when it is 0, 0, which has not been covered, we should be having a default value of all 0, which is the true. Then we have these cases covered 1, 2, 3, 4, 5. So 6 and 7 should also be 0, which is true. 6 and 7 are also 0. And the other ones like 2 or 1, 2 is this value here, and we are getting that correct output. So this decoder is also behaving as we expect. So this decoder, you can this decoder could be altered and changed to cover the decoders that we were talking about here. This is a decoder, this is a decoder, and you have I think 2 decoders in this one. Yeah. So so that's how you would alter a code like that, and then make these modules for decoding the opcode bits or decoding the ALU control bits which are coming from here. All right, so next we're going to talk about the adder, subtractor, which are part of the ALU block which we saw earlier. So that's a half adder there. You can see the truth table and the structural connection. Basically one AND gate and exclusive OR gate, and so that would be, it's just like a a decimal adder. Excuse me. But in the binary manner, when both the inputs are 0, the sum is 0. When one of the input is 1, the sum is 1 and the carry is 0. But when both of them are 1, sum is 0 and carry is 1. That's a full adder, and it can be made using 2 half adders as shown here, and plus one more OR gate. And that's the truth table of a full adder. Again, you can see, so the full adder has 3 inputs, unlike the half adder which has 2 inputs. So it has A and B input plus the carry in input. And you can see this is the truth table for that. A, B are, going, from 0 to 3. And C is going from 0 to 1 for all the, so total of 8 combinations. And basically we go from 0, 1, 2, 3 all the way to 7. And that's what you would be expecting from a full adder. So this is a diagram from Wikipedia. Excuse me. It's showing how to implement a full adder, a 4-bit adder, and also a subtractor. If you recall in binary logic, perhaps if you've studied binary numbers, when you want to invert a number from A to minus A, what you do would be, invert all the bits and add 1 to that. It's called 2's complement. So 1's complement is invert all the bits, and 2's complement is add number 1, binary 1 to it. So that's what we do. So when D is 1, you can see all the bits get inverted from A, because we are using an inverter in that case, and we have the inverted bits of A0 to A3 here. And because D is also a carry input, so that is going to be acting as a plus number. So this will, in case you want to do subtraction, you would assert D as 1 and your result will be B minus A, because A is the one which is getting inverted. But when D is 0, then you would be doing A plus B, because the circuit is for a full adder. So if you want to refer more how this is done, you can go to this link and get more details. But let's look in terms of a code, how this is done in terms of code. Again, I'm giving you only behavioral code. in this recording. So let's look at the behavioral code which I've made. So a full bit adder, one full bit adder is a simple statement like this. These are your ports, and these are the two output ports, fsum and carry. These are the two outputs, and A and B, C, A, B, and C are your inputs. So basically, it's very simple behavioral code. I'm not showing you the structural code. You may want to do it structurally as per if it is needed in your lab requirements. And this part on the top is just part of the test bench, and I'm just instantiating the full adder here and then just supplying some test signals to see the result if it is behaving as expected. So instead what I've done is I've coded a simple ALU and ALU would be getting this bit. This is the code for the ALU here, and the ALU would be getting these bits, which I was, if you recall, this was shown in the very first main present slide. So these would be coming from the decoder. So so the decoder sends. I'm sorry. These would be coming from the instruction. These will be part of the instruction. So these bits will be coming from the instruction, and so this is not the same ALU like you would be, it's a simpler version of that. So I'm not showing all the, I'm just showing 4 combinations: addition, subtraction, shifting, and bit AND operation. So you can see when my ALU control bits are 0 0, I do addition. When they are 0 1, I do subtraction, A minus B. When I do shift left operation, then I shift A, input A, but I use only 2 bits from input B. And you can see I'm just using the 2 least significant bits. So even though input A is could be 4-bit wide, it could be even bigger than that if we change this parameter here. In the RISC processor, you would be using your result would be 64 bits. So this is how you would implement a simple ALU. Let's see how it simulates on EDA Playground. So enable extension. Let me go to my playground. I was away for some time and I came back. So simple ALU, there's one. So this is the same code I was showing you on that notepad, and this is a test bench to try a different combination. I'm using some random values here, line 23. So let's run it and see how does it behave. And actually, if you see, so as you see, when I ran the code, this is what I got on the terminal window in my log. And you can see when my ALU, the ALU control, which is this one, for some reason I'm calling it select, should be ALU control. And when it is 0 0, I supply these two numbers 2 and -1, and I'm displaying them as signed values. Here you can see line 25 signed. So so this would be addition. So 2 minus 1 would be 1. That's what we get. The second, when it is 0 1, which is the subtract operation, so -3 minus -5, which would be -3 plus 5, so the result is 2, which is also good. And the next one is shift left. Like I said, only 2 bits. So this is, we have to shift this, which is number 3, which is basically 1 1 in binary. So when we shift it left, but using only 2 bits, and B is 5, which is 1 0 1. in binary. So we really shift, we use only 2 bits, least significant, so 0, 1 only we use. So we shift 1, 1, which is 3 by 1. So 1, 1, 0 it becomes, which is 6. And the last one is minus 5, and with 0 bit, we do bit AND operation, so that will be, result will be 0, and that's why the result 0, which is line 44, also goes high. So when result is 0, this bit, so this could be like a status 0 in your ALU. When all the result is, the result of your addition, subtraction, etc. is 0, then this bit is asserted, which is typically used as a status bit in the CPUs. All right, so looks like this is also good. So let's go back to our presentation and talk about the other modules. I think we have covered the combinational blocks now. So let's now talk about the sequential blocks, which we'll be using in our top level CPU. So again, this is the sequential logics here would be for these registers and this memory also. But for pretty much everything else, we use combinational logic, as we have already gone through. So let's go back to the D flip-flop, which is basic building block of a sequential logic. So edge-triggered D flip-flop is widely used in digital logic design. On the active edge, which is usually the positive edge, it can be negative also, but mostly it is positive. The D input becomes the Q output. So D input, the Q output, grabs the value from whatever is on D after a small but finite delay, which is due to the delay of the transistors, the gates, which make that flip-flop. For let me just check something. Yes, I am recording. So let's go back here. For rest of the time, when we are not, because we use a clock, so the clock will have the edges only, during the rising edge or a falling edge. The other times when it is not the active edge, Q will hold or store its whatever value it already had. So the previous value of Q will stay there. So the array of these flip-flops can be used to create multi-bit registers. Remember, we are using those 32-bit register file in our CPU. So once we understand how a D flip-flop works, we can make an array, 32-bit or 64-bit long, these arrays of flip-flops, which can make, in our case, we need 64-bit long, because each register is 64-bit long. So let's see. So this is a symbol of the D flip-flop. This is the input. This is the clock edge. When it is a negative clock edge, some cases, like I said, we use that. Typically there's a dot or a bubble here. This is a set input, reset input. This is your main Q output, and this is the invert of Q output. So this is the truth table. The active edge is rising edge. So you can see when the rising edge is happening and D is 0, Q becomes 0 after that small delay which I mentioned there. So it's a minute delay, but still it takes some time, and usually it is nanoseconds or so, and then Q becomes same value as D. Similarly, when there's a rising edge and D is 1, Q becomes 1, and the other times, or when it is high level or low level, or there's a falling edge, then Q just keeps its value, and doesn't matter what D is that time. If reset is asserted, sometimes these are active high, that's as shown here. They can be also active low. Again, they'll have a dot here in those cases. So when reset is asserted, Q will go low, and when set is asserted, Q will go high. This last case is typically not used. This is not a recommended state. So either you will assert reset or set, and Q will change according to that. So here's the timing diagram of behavior of a D flip-flop. This is a link I got it from. All this information you can refer for more information. But you can see when set is asserted, Q goes high. When reset is asserted, Q goes low. when the rising edge of the clock happens, Q gets the value of D again, and here D holds its value, Q holds its value. Like you can see, D changes, but Q does not. Here on the next edge, Q, because D is again 1, so Q stays 1, and here you see this is where Q goes low, and so on. And Q bar is just the opposite of Q. So that's showing you a behavior of D flip-flop. And like I said, we can make an array of these and to have registers. So let's see, I think in my code I created an example code. So let's look at that and how it behaves. So let's look at playground, memory model we will look at later. Yeah, D flip-flop demo. So let's look at the code, and D flip-flop is here. So again, the code is quite simple. This is the code for the D flip-flop. You just have your ports defined. You define your ports, their sizes, any QB is just the opposite of Q, so that's what a simple statement does. And this is the main block for the main code for the D flip-flop. If reset is asserted, in our case it is a low active reset, active low reset. That's why we are looking for neg edge. Q is 0, else Q is D. That's all we need to write. So Q changes only when the pause edge of Q changes only when the pause edge of clock occurs. So this block keeps on running every time there's a clock edge, and clock is could be running at 50 megahertz, it could be running at 100 megahertz, even gigahertz, depending upon the chip you are in. So and here I'm just making an instance of D flip-flop, and interestingly, Verilog allows you to use changing the parameter of the parameter here is 1, but when I instantiate D flip-flop, which I'm doing here, I can change the parameter of D flip-flop with size, which I've changed it to 4. That's what I've done. So now this whole this instance, when it is created, will be 4 bits wide, and then we'll run this test bench code here, and let's see what do we see. So code is same, code is there, I'm running it, and I think I've enabled waveform. Yes, correct. So here you can see when the rising edge comes, when the clock rising edge comes, whatever is the value of D in, which is 1, Q out gets 1. Again here, clock rising edge, D is, D input is D. This is an hexadecimal value, which would be, I think, 13. Yeah. So that is D here again D, so it stays that value. Here input changes to C, which is 12, so it changes to C, and so on. So that's and because we are using a 4-bit input, that's why the input now you can see has from single bit it has become 4-bit input and 4-bit output. So this is how D flip-flop behaves, like shown in this slide also, PowerPoint, and that's what we see in the simulator also. So like I said, we can so that the code I just showed you, it's a 4-bit register. So you can easily make it a 64-bit if you want. So memory is another block, sequential block, which we need for making the RISC CPU we talked at the beginning. So simple memory is made up of by a 2-dimensional array of flip-flops. So we already talked about a single dimensional here, how to create one, and in the code we did that. So if you have a 2-dimensional array of flip-flops, we can make a memory, a read and write memory we're talking about right now. So the first dimension defines the data size or the width of how wide the memory is going to be, and the second defines the address size or the depth of the memory or the number of locations. So the data bus could be common or shared, like we could be using the same data bus, or we can even have a separate, like input data bus for the write data, and output data bus for the read data which has been read from the memory. Memories are usually clocked, but not always. But in the case, I think in your RISC code that you guys will get, quite likely it is not clocked memory, but the one which I'm showing you is clocked one, and usually they are clocked. Typical controls are, of course, controls are through the address bus, which defines and whether it is enabled or not, whether we are going to do a read operation or a write operation. So this is how you can see, this is a block diagram of a simple memory. You have an address decoder. So if it is the address is only like 3 bits, for example, so we obviously can have 2 raised to the power 3 means 8 different locations, 8 memory locations, as you can see, 0 to 7, and the data size is 8. So we have a 1 byte, so a byte organized memory array. So when the address is 5, which should be pointing to this location, and if it is a read operation, and here we are, I think looks like we are showing a shared data bus. So whatever is on the data bus gets written to the location. If it wasn't a write operation and instead was a read operation, or write was low, sometimes the same bit is used for read and write. When it is high, it could be write. When it is low, it could be read. So if this were a read, then we would be just reading this value and putting it on the bus or whatever other registers. So this is, other register the address bus was pointing to. So this is how simple memory is organized. And here again, clocks are not shown, but typically, these operations are usually they are done using clocks, and these are D flip-flops here, array of D flip-flops. So again, the block diagram here shows the address bus, data bus, which is a shared in this case. The controls, chip enable, read and write controls. Clock is not shown. Sometimes same clock is used, sometimes different clocks, one for the write side and one for the read side is also used. So this completes, the sequential logic. So let's now, the memory, go over the memory code, and this is the code for the memory, and this is code for the memory, and a simple memory clocked, and I have these ports. This part here is just defining the ports, input, output port, the sizes, address width, data width, and this is the memory, the two-dimensional array I was talking about. So this is the defining the data width, how wide each location is, and this is defining the number of locations, which is based on the address width. So here we have 8 bits for the address. So 8 to 2 raised to the power 8 to 56 minus 1. So we'll be going from 0 to 255 locations. So 256 locations in all. So the code is pretty simple. The code is here because it's a clocked memory, like I mentioned. So on the clock edge, everything happens on the clock edge. When reset is low, and so we were just here we are just when reset is low, we are just initializing the memory and filling all the locations with 0. And data out, which is a bus coming out from the memory output port. I have 2 separate ports, data in and data out. So that is also 0. But when reset is not asserted and clock edges are happening, pause edge of clock, this code is running, and then we check if memory write has been enabled. If it has been enabled, then the memory content of the memory at that particular address becomes the data on the input bus. Otherwise, if it is not a write operation, we assume it is a read operation, then the data out, which is the outgoing bus, gets the content from whatever the address is. So it's a simple code, nothing complicated, and that's how you would write a memory block using Verilog. And this code here is just a simple test bench to give some random values to data in, increment our address, for two cases, once when we are doing the write and the other time we are not doing the write, so which we are doing read. So let's see how does this code also run on the EDA playground. So I go back there, I go to my playgrounds and memory model. So so like I said, same code and same test bench. So let's run it, and I'm using this waveform. To run this waveform, you have to add in your top level test bench these two lines. So these two lines are needed. They are in the code also on the other side. So let's run this code, and I'll show you what I was talking about. Yeah, these lines. So you have to add these lines if you want to capture that waveform. So waveform, it has run, it has outputted some values here, and let's look at the memory, how the memory is behaving. So we are doing write enable. This is write enable. It's high, and then we are reading the memory. So we are supplying some random data, and because it is clocked, and you can see addresses incrementing, to 50, 0 to 15, and then back again to 0 to 15. And you see on every clock edge, rising edge, the memory getting filled. The memory is not captured here for some reason, because it's not part of the test bench, it is part of the instance. But we can confirm that when we are reading the memory. So here you can see we are reading the memory, and data out is when we're reading location 1, value is 4, which is what we wrote here. Then the next value is FFF1, same here, FFF9, and so on. And the numbers keep on repeating. D is on during 2 locations, we see that, and then C and 9. So the memory is behaving as we expect. So and again, the values are also shown here, and you can see every time the clock edge occurs. Clock edge is this one. It's not easy to understand, but I find it easier to understand it here. That's why I prefer using waveforms also. But if you were to dig into this, you will see the same. We are writing those values 4, FF1, FF9 to these locations, and then when we are reading, when the read bit, which is the third one, 1, 2, 3, when it is low, again when we are reading location 0, we read 0, with location 1, 4, and so on. So you can correlate this also to what we are seeing here. So it's always obviously easier to figure things out. So let's go back to our presentation, and that's basically it. So we have covered we've covered in today's present recording these combinational logic, adders, like we have here, shifters. I showed you in that ALU code how to do shifting. We covered decoders, various decoders that we have. We covered a small ALU register file, only 2 4-bit wide in our case, and memory also. So we've basically covered all the blocks, and in the next recording, which I will do, I will show you how the interconnection of all this is done at the top level, and how to run a simulation of the top level. So that's it for this recording. Thank you very much, guys. I hope this is useful to you guys. Thanks a lot.